There, this is a demonstration of my final project for feedback and hardware interfacing. I'll go ahead and give a quick demonstration of my robot and how far I've gotten with it. So I'll first turn on the Arduino by plugging in this 9-volt battery here on the side, and the motors on the bottom are going to be controlled with this, or powered by this LiPo battery. So you can see a little demonstration of it balancing. You can see it's a little bit too bouncy. I'm having a little bit of issues controlling the PID values, but it is balancing for the most part. I had a few changes from my initial design, mostly due to the fact that I wasn't able to get this properly calibrated. Initially, I had wanted to incorporate this IR sensor right here to be able to drive the robot forward and backward and be able to turn it. But since I wasn't able to get it to balance, I unfortunately had to leave that component out. So this is the overview of my self-balancing robot. The components that I used are listed here in the list. The only thing that's a little bit different from the diagram that I provided here was the 3S LiPo battery and the 9-volt battery. I was just having a hard time finding those components on Fritzing, so I replaced them with the AA batteries here. The diagram is a little bit different just in the fact that the 9-volt battery and the 3S LiPo battery are not wired together. These leads right here would represent the leads going to the 9-volt battery powering the Arduino, and these leads on the right here would represent the 3S LiPo battery powering the motor driver. So the pins that I initialize are just for the motor driver, and the libraries that I've included here are just to read the values from the MPU gyro sensor and compute the angles, and use those angles to compute a motor power. Each motor has 2 direction pins, as well as a PWM pin that controls how much power is going to the motor. In the void setup, I start by just initializing my baud rate to 9600, which works well for the MPU sensor, although most people recommend using a little bit of a faster baud rate. The motor driver values are just set as outputs, and then I initialize the MPU and set these offsets. These offsets are a little bit wrong just because the center of gravity of my robot is a little bit off from being completely level with the ground, which is how I had it when I calibrated it. And then at the end here, we just initialize the PID sampling. So in terms of reading the MPU gyro sensor values, it's relatively simple. It's just these 3 lines of code. It is a bit counterintuitive, but the acceleration values here are actually based on the given angle at any time, and the gyro x value is more based on the acceleration. Now it says over here that the initial angle values are given in degrees, but they're actually given in radians. It's a typo. In terms of calculating the values here, we start by just converting the acceleration values from radians to degrees. The gyro rate is then mapped from these 2 values here, the 32,767, down to a range of negative 250 and 250. And then we use that along with the sample time to figure out the gyro angle. The gyro angle and the angle provided by the acceleration are then used to calculate a more accurate angle measurement that includes motion. And then that value is brought down here, and the error is calculated from the target angle. The target angle right now is set to negative 2.5, so it's going to keep going until it gets to about 2.5. And then the error sum is constrained from negative 300 to 300, and all these values up here are combined along with the P, I, and D values to calculate the motor power. The PID values are really what essentially control how well the robot balances. And then at the end here, the previous angle is just set to the current angle, just so when it reiterates, the previous angle is the previous angle. This little loop right here just essentially controls the PID values. I'm not 100% sure how it works, and I believe it's a bit beyond the scope of this class, so I'm just going to go ahead and skip on over it. The void loop here is relatively simple. You just read the three values that we were talking about before, and then the motor power is calculated in the previous slide that we showed. And then it's just constrained from negative 255 to 255 because they're PWM values. And then the set motors sends the motors over to a separate loop to drive them. So those values are sent over to this loop. As mentioned before, each motor has two direction pins and a PWM pin. These if statements essentially just check if the motor speed is set over 0 or below 0, and sets the direction pins accordingly and tells the motor to drive by the motor speed provided. The left motor here was increased by a factor of 1.4 or 1.3 just to match the speed of the right motor because there's some manufacturing errors. These three values right here, the KP, KD, and KI, are what control how well the robot balances. The KP is proportional power control. Essentially, the more you tilt the robot, the more power it's going to send to the motors. KD controls how quickly the value changes so that you don't overshoot the balancing. And the KI essentially controls how sensitive the whole robot is. So if you tilt it just a little bit, it corrects itself. And if the value is too low, then you'd be able to tilt it too much before it corrects itself.